Good morning, Sunil.
Good morning, Sanjay. Good morning, Sunil.
Good morning from the
Very good morning, everybody.
very good to everyone.
So we are all set. I missed yesterday's class.
It was this, so on the second part of the squeeze state and some experimental
Yes.
care was there. So how to
Yeah, yesterday. It was a very tight day for me, and I not only missed the class, I was not even able to catch up on the YouTube. So I was hoping to do that. So I think I'm going to be a little lost today, but I'll try to follow.
no.
I missed the class yesterday, and I was not even able to catch up later on the YouTube, which I had intended to do, but it turned out to be a very tight day for me. There were just too many events, one after the other.
Oh.
Yeah. So it's nearing time, just a minute to go. Sanjay, you want to share your screen and
Trying to test it.
yeah, just set it up. There are some very good participants in this class. Yes, good. You want to go full screen, I think.
Yeah, I'll go to full screen.
So we are well into the course now, and let me welcome everybody once again to the continuation of this course. And if Sanjay and Sunil permit, we can actually begin. It is time.
Yeah, it's a time.
Yes, sir. Sure.
Yes, Sanjay. So please continue your lecture series. It's a delightful lecture series. So many of us are benefiting from it. Thank you. Yes.
Thank you. Thank you. So it's a hearty welcome for the 8th class. So good morning, everyone. So I believe that you have at least glanced some of the slides which are you could see actually could grab some of the things which are discussed in the last two classes on the squeeze state. So we have given some brief demonstration how to make the squeeze state. Okay. And today afternoon, I would like to say that there will be a tutorial session. So at 3 p.m., please try to attend that. Okay, there are a lot of questions given in the assignment which will be discussed. Also, if you have any other questions regarding the classes, okay, also you can raise that. So here, what I would like to discuss today is something which is a continuation of the squeeze state, but it is actually will give you some kind of statistics of the photon. As you have seen in the last class, that what we have discussed that the squeeze state, which is a purely quantum in nature, okay, you have to see that quantum feature when your fluctuation of the density or fluctuation of the number density, okay, which is less than a square root of the mean value of the number density. And what we have seen that this is the scenario which is possible in the case of sub-Purcinian cases. And in the Purcinian cases, what happened? These two, the fluctuation, okay, will be equal to square root of mean value. That means that variance and the mean will be same. So according to this understanding, okay, what we can do that, we can easily go through that distributions of the photons, okay, for different kind of lights. Like if you have a coherent light, okay, what we have seen that it follows the Purcinian distribution, and the Purcinian distribution case, that is a property that the variance is equal to mean. So in bar is not properly seen maybe, but I don't know why it is, but it is in bar means the mean value of the number distribution. Similarly, what you saw that just now that for we can see that sorry, this is the wrong thing as written, not chaotic. The quantum light, okay. So for that, actually, you will have that delta n less than equal to square root of n bar. And for thermal light or chaotic light, so it will come here, the thermal light or chaotic light, what you'll see that you will get that fluctuation which will be more than your square root of mean value of the number distribution. Or you can say the variance will be larger than the mean values. Okay. And we'll try to see that whether really it's true or not. So these thermal light, which you see classically, like blowing up the bulb, okay. So those are actually classical lights, okay, and they follow superposition distributions. Whether the laser lights, okay, what we just discussed so far, okay, those are actually that obeys the Poisson distribution. So for the quantum light, which has actually quantization features, okay, inbuilt in that, so they actually obeys the sub-Poissonians. So if you want to see that if you would like to find out that in that particular distribution of the light, okay, any of them, either coherent light, thermal light, or chaotic light, okay, or quantum light, okay. So if you want to see that your number distribution, okay, so what you will find out that this x-axis is the number of photons, okay, and if you have the mean value of the number of photons is 100, so you supposed to see that the peak value of a distribution, okay, will be at the 100, and there will be some kind of distribution around this mean value. And in the case of the Poissonian, what we just saw that since n bar is around 100, will be almost like a normal distribution, okay, so it is large values, okay. And but once we go for the sub-Poissonian, okay, the spread, that as we are saying the sub-Poissonian spread is very narrow compared to the mean values, square root of mean value. So what you will see that the spread will be narrower, okay, and you will have the more density or more population will be in the near the central values compared to the Poissonian and super Poissonian cases, where actually in the latter case that you will get more spread, okay, in the distribution of the number. So this is the feature which you will see for the different kind of distribution. Now, when you want to detect this kind of a distribution, whether they are really true or not, okay, so then how to start the approach. For that, what you do that, we are trying to, let's say that, going for a sub-Poissonian cases. And but this kind of a distribution, as you know that we have to count the number of photons. And for counting number of photons, it is wise to use some kind of low intensity beam. Okay, and here if you are just shining low intensity beam on the photomultiplier tube or avalanche photodiode kind of things, okay, what would happen that over time you will see that signals are coming, which are coming as a current, because it is a photomultiplier tube which is converting, okay, a photodiode is converting to current, and we are getting that over time the different value of current, okay. If we just integrate over a particular time scale, and we want to just do the integration over this kind of time period again and again, and see that what kind of statistics the output signals gives. That is over the integrated time, okay, what will be the value of the output? Okay, and we would like to see that over the time being, how the distribution, okay, follows. So that is the goal for that. So here, what we just understood that if we shine the light on the photomultiplier tube, so if we have an intensity I, and if we have the cross section A with the photons are coming with a frequency omega, what we can write that flux will be nothing but IA times H cross omega. But that flux actually will not be converted to current because you will have the efficiency of the detector, okay, which has to be taken care of by the eta factor. So when you just count the rate, okay, number of photons coming, okay, by over time, okay, we have to understand that you have to multiply with the efficiency factor of the detector, and that actually will be the count per rate per second. Okay, so that is the way actually once do the experiment. We'll see it in details. Okay, but before that, what will be ideal to just understand, as we said that the thermal light or chaotic lights, they follow superposition. So can we understand them? So let's look at for the thermal light first. So if we want to see the thermal lights, this is nothing but the light we get from the black body radiation. And if we want to calculate that number of photon, okay, in particular mode, so the Fowler distribution, as you know, that follows Boltzmann distribution. And this is the nothing but that e to the power minus En by kBt, kB is Boltzmann's constant, and where En is nothing but for that particular mode, the energy will be in H cross omega. Omega is the frequency of the light which is coming, divided by summation of all the modes. Okay, so that's actually giving you the probability. And if you want to see it carefully, so compared to the Poisson distribution, as we have discussed earlier also, which is for n values, mean value of n is 10, which is almost like a Gaussian or normal distribution, that what would happen that you will see that that we can write x equal to e to the power minus h cross omega by kBt, then that numerator will be able to write x to the power n. And in the denominator, it will be summation of x to the power n. And the summation of x to the power n, which we can write 1 minus x to the power minus 1 when x is less than 1. Okay, so here x will be less than 1, and then what you see that as n increases, okay, these functions actually decays, and that is the things which we see it here, that in the thermal distribution, okay, with the number of the photons, okay, that distribution decays. So that actually shows that how these thermal radiations, okay, distribution happens, okay, over different number of photons. Now let us check that if that what we said that the variance or standard deviation, how we can calculate from it. So if we just find out that what is the mean value, so it is nothing but that since we have a distribution given to us here, okay, we have just multiplied the n and sum over all modes. Okay, so if we just do that, what would happen that we'll get x by 1 upon x. Here small tricks are applied, which you can just look at the Fox books and find it out, that if you write that summation of n x to the n, as you see it here, x is nothing but this one. And so what you got it, that you got p and w is x to the n 1 minus x, and from the summation you can take out the 1 minus x, and what will be left with the summation in x to the n, which is written it here. And this one is nothing but you have to just take the derivative of this quantity with respect to x. So then n will come in the front, okay, and we will have, since the summation is from n equal to 0 to infinity, okay, what we will get that you can get the summation back, okay. And this one was summation of x2 by n for small value of x is nothing but 1 up by 1 up minus x. So what you saw it, you saw that you got this one, which you can do the differentiation easily and find out this expression, because in the denominator you will have 1 minus x square after the derivative, which will be cancelling that outside when you have the 1 minus x is there, and ultimately you will get x by 1 upon x. So this one is showing that if you just replace x by this exponential factor, okay, and divide by this factor, okay, what will you have? You will have 1 minus e to the power minus h cross omega by kbt minus 1. And I believe that you are able to now recognize these things which is independent of n, okay, and so that is expected, okay, and that means that all the photons are lying in the particular energy levels, and this actually follows the shows the Bose-Einstein statistics. Okay. So you have seen that the mean values actually follows the Bose-Einstein statistics. Now, once we have understood the mean value, what we can just see that if you want to calculate the variance, okay, you have to calculate first, you have to calculate n square mean value. Okay, so that means that you have to just multiply n square with your number distribution and sum over all the modes. Okay, and these will give you just have to work it out little bit. Okay, 2n bar square, the mean value of n square plus n bar. So what it does means that if you want to calculate the variance, which is n square bar minus n bar square, and what we'll get, this is nothing but n bar square plus n bar. So in the case of the Poisson distribution, what you had got actually that the variance equal to nothing but n bar. Here you are getting additional term that n bar square. So that's why that what we said that in the case of the thermal radiation or black body radiation, which is a classical light, okay, your variance is more than the mean value. Okay, it is the extra terms will be there in bar square. Okay, so for details you may just look at the Mark Pulsbook's page number 83, 84, where actually all the derivations are given in detail. So I believe you have understood for the thermal radiation, which is classical light, okay, for them actually the variance is more than the mean value. So that is called superposition distribution. And now let us look at the when you have the Poissonian cases, and Poissonian cases uses a variance equal to mean. But our interested to look at the subpoissonian, where actually you see that quantum signature of the light. Okay. And in the case of subpoissonian cases, what would happen, as we have seen that the fluctuation is less than the square root of mean value, or other way to say that it is actually variance is less than the mean value. And so point is that for this experiment, to do the experiment on this, what we should look at. Okay, so that first of all that this kind of light, as you see that this will have a less dispersion compared to the laser light or Poissonian lights. Okay, and once you have a less dispersion, that means that light will be more stable. Okay, just let us see that in terms of a trivial example to understand the subpoissonian status, how we can understand the trivial example which I'm saying. So let's think about that. We have all played in our maybe childhood that marbles. Okay, so glass marbles. Okay, you are aligning them over a bar. Okay, and drop one after another marbles from the bar. Okay, so this is the picture which you can just visualize. So that what would happen that once you just make some inclination of the bar, okay, what would happen that your marbles will come to a bucket which is lying in the down. Okay, one after another. So we are looking for this kind of an idealistic scenario, okay, where the photons are coming one by one. It may not be practical, but that will be one of the trivial example of the subpoissonian cases. So it's like that. If you can imagine that you have a tube, okay, through which the photons are coming, and with a equal time interval. So let delta t is the equal time interval, let's say. And we know the photon's speed is c. So the distance between between this photon pair will be c delta t. And that distance will be equally maintained for all the photon pair. Okay, and these photon streams, okay, they are coming and to the detector. You can imagine like that. Okay, so that it is like a uniform rolling motions. Okay, so if we just want to see the statistics over a time period t, what would happen that in the detector, when you want to count that, let's say that you are counting over a time period t. Okay, so and this is coming at a rate of delta t. So what would happen that the photocurrent detection will be that t by delta t, and that will be multiplied with the efficiency of the detector, and whatever the value will get, the close to that whatever integer value will be the photocurrent. Okay. And that, as we see that the photons are coming with the equal time interval. Okay, so we expect that this is almost constant. Okay, for every detection, every hit. Okay, now this is not so easy. Okay, that's because that here what we see that photon streams, they follow, okay, kind of something called nothing but a number state distribution that is fixed. The number of photon per part that state is fixed. Okay, so the number states are nothing but the purest form of the subperfection light. But it is very difficult to observe the number state. Experimental is really, really challenging. Okay, so and also that you remember that since it is almost constant, your detector efficiency will be very good. Okay, over time to detect these kind of things. Okay, so in this kind of a scenario, simple trivial scenario, what would happen that if you want to see that statistics, okay, you will see that your photons are coming, okay, in particular values only. Okay, so that there will not be any other variations. Okay, only in the what a particular value of n is coming over a time period t. Okay, so if you count that, if that is a delta t is, let's say that it's 2 millisecond, and you are counting that capital T is 10 millisecond, so you will get the value 5. Okay, here in bar. Okay, so that and that will not vary. Okay, so that your distribution is like a delta function kind of things, or just is a fixed point, even if not delta function. Okay, so what we get it that you get this kind of a fixed distribution. Okay, and for this kind of fixed distribution where n bar is the value in itself, and your fluctuations, okay, mean value of fluctuation will be 0. Okay, that means that here what will be the idealistic kind of scenario where your fluctuation is less than square root of n bar. Okay, or variance is less than n bar. Okay, so that means this is one of the simplest and trivial example for the subquotient distributions, but it's not possible to, I'll say that not possible to demonstrate in the experiment. It will be very difficult. Okay, but close to this kind of scenario, it is possible, as we see in the next few slides. Okay, so what is actually what we are going to see is that that it is possible to make the photon stream, though not in the equal time interval, but for a time interval which is not, may not be exactly matching with each other. Okay, so it will be close to that, but not the, may not be equal time interval. Okay, so and it is not that bad that it is like a random. So in the case of random, if it is, then it will be Poisson distribution. So if this figure will tell you that this what will be the distribution looks like. So in the case of Poissonian, what would happen? So you will get what would happen? You will get here one photon after you just place an attenuator to just count the number of photons. Okay, in a small number. So if your laser pulse is coming, you are placing an attenuator, okay, and after that you are detecting. So you get one photon, sometimes you get two photons, you get another, you have to wait for many pulse, okay, and get another photon. Okay. So you see that they are coming random. There is no kind of a systematic approach or okay. Whereas if you see it here, what would happen? It will looks like that. Here you got 4 of them. Here you got 3 of them with one pulse gap. Here the 2 pulse gap you get again 4 of them. So there is some kind of a periodicity of the periodicity of the heating. Okay, is or periodicity of the detection is we are able to get it. So this kind of periodicity, if you just get it, okay, then we will be able to reach the subversion distribution. So I believe you have at least got some kind of idea that how to visualize this subversion distribution. Okay. So once you have got some visualizations, okay, then let us see that whether we can understand them, okay, in terms of something called coherence of the light. Okay. So what actually we want to before going to talk about the experiment, we want to discuss that something which is very important for that experiment is that if we can see that temporal coherence, okay, over the time, time how much the coherences exist in the light or not. So if we would like to look at that, okay, this is all because we would like to look at the subversion distribution of the light. Okay. So for that, actually, just let us know a little bit about how these temporal correlations, okay, or coherence, it can be called as correlations, okay, are calculated. In the first order correlation function form, what you do that you just take the correlation, the time correlation, okay, or this is with respect to that E star E is nothing but the amplitude of the light, okay. So over that time gap of tau. So you just observe that amplitude, a light, okay, at t and after time tau, okay. So you just multiply these two amplitude and take that over time average of this, and that you normalize it, okay. And what you will get the first order correlations, okay. So this is nothing but it will give the correlation at the level of fields, okay, how the field is correlated. That means here phase is also important, okay. So here this time order average, okay, which you can write it 1 upon the time period, so that is t, and integrate this function over the time period, okay. So now this is very difficult to achieve or do the experiment in the lab. So instead of that, the people can do it. It's not that impossible, as we have discussed some kind of homodynamic experiment in earlier, okay, which is used to discuss that first order correlation, okay, or which is used to show, demonstrate the first order correlation. Let us not get in that. Instead of that, what will be simpler, okay, to detect is that second order correlation, and which is known for long time, okay. And what is the definition of the second order correlation? So you may know that, or you may realize from the first order correlation, which is on the amplitude, second order correlation must be on the intensity. So what we can write that your expression will be of time order average, okay, and here E star times E will be there at t and t plus tau, which will be normalized, okay. And this expression we can write in terms of intensity. So it is nothing but that it's like intensity correlation function, okay. So you see that intensity at t and intensity at t plus tau, which is just normalized, okay. So what you saw that second order correlation is nothing but intensity correlations. Now let us see that how it can be done, okay. For this kind of experiment, what actually you have to keep a very close observation is that your source should be constant, should have constant average intensity, okay. That means that over a time period, okay, source should not change the intensity, okay. It will be almost constant, okay. So that means that if you take the time average of the intensity at T and time average of the intensity, this is for the source, okay, after time tau, these two will be supposed to be same, okay. So that has to be maintained, okay. And also that since we are looking for the temporal correlation, our spatial correlation should be, spatial coherence, I should say, spatial coherence should be very, very good. That means we should choose some small area so that we can believe that over that small area, our light has very good spatial coherence. Okay. So if you can just understood or keep this or maintain these two constraint, okay, what we can look at now, we can look at that coherence time of a particular source, and that we can try to find out using the calculating the G2 value. This is also popularly known as G2 value, okay, that is second order correlation function, okay. For, let's say that if you say that your correlation times is sorry, coherence times is tau c, or you can say correlation times also, okay, then that you want to find it how the correlation function, the second order correlation function behaves over the tau, okay. So that actually we are going to obtain it. But before that, let us see that what would happen after these correlation times, after the coherence times. And we believe that after the coherence times, system will be totally uncorrelated. Okay. So that is, let's see that if that is the case, what will be the expression of the G2? So if it is uncorrelated cases, okay, what would happen that uncorrelated cases, what would happen that, let us see that what will be G2. So here, what you see that you can write your intensity, okay, in terms of the mean value plus whatever the fluctuation on the mean values, okay. So that is that delta I, okay, the fluctuation or standard deviations, okay, in the mathematical form, okay. And if you take the time average of this fluctuation, as you see that it can go plus or minus, positive or negative, so that time average will give you 0. So what you just can see that if you take that intensity correlation terms, so IT and IT plus tau, okay, over tau get very, very larger than tau c, it is easy to calculate. You just replace that I expression from here, and then you just do the calculation, keep the term up to order of the tau only. Tau square terms is not necessary, okay. So then what you will see that this is nothing but I square, okay, so which we can keep it as an ascendant. So if this is the I square, okay, that intensity correlations for tau very, very large than tau c, then what you see that in the from the G2 term, okay, that if you see, look at that when tau very, very less than tau c, that numerator and denominator both are becoming same, both becomes I square, okay. So that will mean value of I square, okay. So that means that you will get the 1. So what would happen that G2 function when if you look at the after much after that coherence time or collision times, okay, this will be 1. So that actually you have to keep in mind, okay. So in the case of uncorrelated cases, okay, G2 is 1. So once you have got this, G2 is 1 for tau very, very less, greater than tau c. So let's see that what would happen when tau equal to 0, which is less than tau c. So one of the, just for curiosity, and which is easy to calculate. So if you replace tau by 0 here, what would happen that you'll get I square in the, and you have to do the time average, okay. So if you do time average on I square, and here what you'll do that you average the intensity and square, okay. So at when tau equal to 0. So what would happen that whatever the fluctuation of I has, if you square it up, all becomes plus. So all positive. Okay. So you expect that, okay, that this will be much more than the mean value of the intensity. So when you just take the time average, okay, this will be more than the denominator values, the IT square. And as you have just realized that since the numerator is much more than the denominator, okay, these will be greater than equal to 1. So this is truth, like that at the initial time, okay, when you are looking the source, okay, and at that time, if you just see the G2 function, the way G2 is defined here, so this value will be more than 1. And what you can show that, so that will be the maximum values. As you see that as you go away from that tau equal to 0, you are expected that the correlation will deteriorate or coherence will deteriorate. And at when after a time tau c, it will become totally uncorrelated and it will become 1. So what you will expect that that G2 at 0, tau equal to 0, will be maximums. So we can just see that in the profile, how it varies, the G2 varies over different values of taus, okay, in the next slide. Okay. Now, in the case of perfectly coherent monochromatic light, okay, so if it is perfectly coherent, okay, what we say that there's no fluctuation. So that it's a delta I maybe over time period it will be 0. Okay, and then what you can write that your IT will be same as, or IT plus tau will be same as IT, and that is constant. It's I0. So that means that if you put that here for the perfectly coherent monochromatic light, okay, this will become what you say. This will become 1 again, isn't it? Because both are the terms are same, and what you'll get, and it says there's no variation, there's no positive, there's no negative terms. Okay, here unlike here, okay, so these though we'll get same terms, but there's no variations. Okay, so then there's no variation, both numerator and denominator will be same, and we'll get 1. And that is the feature which you'll see it here. So when there is a coherent light, okay, perfectly coherent, we'll get that G2 is 1 throughout the time. But as he was just got that tau equal to 0, we'll get some maximum value, and after that slowly deteriorate. And when tau becomes tau c, okay, or more than that, okay, it becomes once again, as we have understood from the expression. So in this period, okay, where actually it was large and coming to the coherent, okay, that is actually a superposition, or some people say chaotic region, okay. So of the light, okay, and after time tau is greater than tau c, okay, it settles down. The G2 will be settles down to the, or it will merge with the coherent profile, okay. So that is the statistics, the correlation statistics we see. Okay. So initially, what you see that it comes from the largest value, G2 0, and slowly it will come down, and it will be saturated with the G2 equal to 1. So let's try to understand with a simple example, which is also given in the Mark Fox books. Okay, so some expression of the intensity, if we can consider. Okay, like let's consider that it is in the 6.1 example given in the Mark Fox books. Okay, so if you consider monochromatic light, okay, and whose intensity modulation is like I naught 1 plus a sine omega t. And you know that if you take time average of sine omega t, it will be 0 because it's oscillating. Okay, so it will be 0. And then if you take that time average of this intensity, it will be nothing but I0 will get. Okay. And if you calculate the G2 function, okay, since you will, if you just in the denominator, you will get a mean value square, so it will be I naught square. But whatever numerator, you will have a square of this quantity, which you will take the time average. Okay, and since the I naught can be coming out, so it will be cancelled, and you will have the time average of this function. And the time average of this function, if you just calculate, which is turns out to be 1 plus a square by 2. Okay, so that's easily you can calculate. Okay, so once you calculate this one, what you see that at G2 at tau equal to 0, okay, so it will be more than 1, okay. So this is that what we calculate at G2 at tau equal to 0. So it will be more than 1, as A can be positive or negative, whatever it is, or it can be 0 when A equal to 0. And as you know that A, okay, since it's talking about the amplitude variation, okay, so then the value of the A maximum is 1. So that when A equal to 1, we'll get the maximum value of G2. And that is 1 plus half. Okay. So the G2 of 0 in this case is 3 by 2. Okay. So what you got in the simplest example of this intensity profile or intensity modulation feature, okay, that we saw that G2, okay, has to be at 0 has to be greater than 1, and it has a maximum value, okay, which is 3 by 2. So this is the simplest example. So what we understood so far? So we have understood for the classical lights, okay. So this is the parameter which actually we should always look at, that at tau equal to 0, what is the correlation function or at second order, okay. And in the second order correlation function, okay, at tau equal to 0 for classical light will be greater than equal to 1, okay. And these will be always, okay, that this G2 of 0 will be always larger than for any other tau values, okay. And for a perfectly coherent light, it will be 1. So this we have understood, okay. Now, if you want to see that what would happen when that G2 will be less than 0, G2 at 0 less than 1. And in that case, actually what you can show that you will get that subquotient natures, okay, the anti-bunching, so which I am just going to explain, that anti-bunching form will be able to see, where actually your quantum scenario will be observed. So what is happening, let's say that this is the example of the coherent light. What is coming, that photons are coming at a random. You see that sometimes 4, sometimes 5, sometimes 2, sometimes 1, they are coming at a random. Okay. So this is coming as a when the photons are coming as a bunch. Okay. And the number of photons in each bunch is different. Okay. Uh, so the so that this will be the coherent length. So this is kind of your chaotic scenario, okay, for the first one. And so you will get this kind of scenario in the case of the thermal light or chaotic light, okay. And second one, which you see that, okay, that when you see that here 1, here 2, here 1, so there is some kind of a closeness of this distribution, but they are coming in very random way, okay. So they have some kind of systematizations, but still the random signature is very much there, okay. So that actually can be understood as uh, as a coherent light. But in the case of the quantum scenario, where actually we see that there is nothing like it, that a bunching of the photons are there. Here still there is some bunching of the photons there, but here there is no bunching of photons are coming individually. Okay, so that's a scenario where actually G2 of 0 will be less than 1, and that is called anti-bunching. So what you will see that to see that quantum scenario of the photon or the light, okay, we should look at the correlation function which is less than 1, second order correlation function, and that is the case, okay, where anti-bunching formed, and we can say that it is anti-bunching distribution, okay. So this is difficult though to do the experiment, but in 1956, famous scientists Henry Brown and Twist, okay, they have working on for the astrophysics purpose, okay, and they have shown the how to correlate the photons, okay, of two coherent beams, okay. So they have shown the demonstration, which is still again that homodyne kind of experiment. Okay, light is coming through the beam splitter, and then they are allowing them to the detecting input detector, and using some kind of a stop and start button, they are able to count it. I'm not going to go details of this. If you want, actually, it's very nicely written in Mark Fox books on page number 114. You can look at it. And what is actually seen that by choosing the proper delay between a start and a stop, okay, you can frame that your time beam. And over that particular time beam, you can see that what will be the number distribution. Okay, so what you see that you do the experiment and see that exactly the kind of things what you see it in the theoretical way, that due to functions. Okay, so here the correlation will be similar kind of things. Okay, and you see that you will get coherent time after time interval. Let's say that coherence time. Okay, so this is the famous experiment which actually shows that, okay, that at the coherence time it can be obtained. Okay, and for the light which is coming from the star, how they behave. Okay, how they are correlated. Okay, now for the anti-bunching, okay, this is really difficult. Okay, and though it is difficult, but it has been demonstrated in the simple ideas by Kimball and et al. Okay, that I just want to briefly explain you that experiment very naive way, so that you will be able to follow. Okay, the first step in this experiment, as you understood, that you want to get the photons one by one kind of things. Okay, or maybe at a time maximum, not two of them, but may not be equal interval, but it will come in the one by one. Okay, so but the time gap may be not fixed. Okay, the between the in between the heating of the photon to the detector, it may vary a little bit, but what do you want? We don't want more than one photon to hit to the detector at a time. Okay, so for that, what we have to do? So we have to get emitted light, and emitted light, for that we have to choose some species which can emit. Okay, and that is species we have to identify, make it separately, or separately situated in an isolated box. Okay, so that you can have that individual atom or molecule or quantum dot which can emit. Okay, make a proper isolation for that. Okay, so that that nothing is close to that. Okay, if you have that particular atom or molecule or quantum dot, and you just allow at t equal to 0 shine the laser light on that. Okay, and let that atom get excited to the excited state. Okay, and wait for the time when the photon emits. Okay, so that now you know that it takes some time to see the photon, because it depends upon the emission probability of the particular energy level of the state. Okay, and that, let's say that emission times is tau r. Okay, so after the tau r, okay, you will be able to see the photon. So it's like that, this picture. Okay, over a time, if you just see at t equal to 0, you excite the atom to the excited state, and then what would see that at that time t equal to tau r, okay, you see that the first emission took place. Okay, and once the emission took place, so what would happen? Then atom will come back to the ground state. Now you have the continuous source of the laser light. Once the atom comes back to the ground state, again it will absorb that light, because till it was there in the excited state, you are not matching the frequency of the laser light, and the absorption frequency is not matching. So it will be just going through. Laser light will be going through. Okay, it will not be absorbed. But once the atom comes back to the ground state, it will absorb light again, and again it will go excite. Okay, so that what would happen? That once you see the photon emitted, okay, the atom will be re-excited by the laser light, and within that actually takes very short time, because laser light is very strong. That means number of photons are very strong. So your cross section, okay, of the photon for this kind of atom will be very large. Okay, so you will see that within a very short time your atom get excited. Again, it will de-excite. Okay, using spontaneous emission. But thing is, a spontaneous emission actually is a kind of a not it is not a regular. Okay, it is probabilistic. It depends upon the probability of emission. Okay, so that means that the tau are times which you got it, okay, in the first emission time, it may not be same in the second one. But what would happen? But there will be some time, definitely there will be some time. After some time, you will see the photon coming in. Okay, so that what would happen? This cycle is going on: absorb, emission, absorption, emission, absorption. Okay, and so emission, you see that atom absorb the light and going to the excited state. Again, emission, atom absorb light, again got excited, and again emission. So what would happen? For each emission, you'll get one single photon. And though these photons are not coming with an equal time interval, but there is some time interval, and you expect that there's no possibility that two photons comes together. Okay, so that's a very good point, that there's no way that you will get bunching. Okay, so that so you'll see that you will be able to get perfectly scenario of the anti-bunching. The photons are coming one after another, may not be in equal time interval, but they don't come together. Okay, so that it is a perfect scenario of the G2 of 0 is 0. I believe you have understood that experiment, which is very difficult to achieve, but is possible. Okay, and it is done. Okay, so and now you look at that figure again. Okay, there's subposition cases. You see that you got the equal time interval. In the equal pulse, you get the photon. Again, there may be gap, and then again you are getting photon. So you will see that subposition distribution in the case of anti-bunching. Okay. So so far what we have understood the photon statistics. Okay. And if you have any questions about that, okay, that we saw that the different way to understand that, either using the distribution, where you see that different kind of distribution, superposition, Poissonian, subposition, and we saw in terms of second order correlations, where you see that you can understand them in terms of the bunching, anti-bunching, and normal, and that is the coherent light. Okay. So if you have any questions, you can ask after the maybe you can ask after that few more slides, which I just initiate for the next class. Okay, or you can ask in the tutorial sessions. Okay. So now what we are going to discuss is that, okay, we have got quantized light. What do we do? So that for that we have to interact that quantized light with the matter. Unless we can use this quantized light, which actually require the interaction picture, okay, there's no use. Okay, so we need to understand how this quantized light interact with the matter. So for that, just briefly let me explain you that, maybe you all know, but just how this atomic structure forms. Okay, so if you can just see it from a simple example, okay, like a boron, where you have that 2 electron is occupied in the 1s orbital, 2 electron occupied in 2s orbital, and 2p has only one single electron. So if you have this energy state of that, which we can say that doublet p, because it can have the both up spin and down spin, this isolated electron. Okay, and then you can have that LS coupling. Okay, that spin orbital coupling, which actually splits the state. Okay, to the fine structure state. Okay, so where you will get total angular momentum, and in this LS coupling will give okay, for this p, okay, will have total angular momentum J equal to 3/2 and J equal to half. Okay, and then what would happen if you have that the atom has a nuclear spin, let's say non-zero nuclear spin I, then that nuclear spin can couple with the total angular momentum of the electron. Okay, so there will be momentum interactions. Okay, so that momentum, okay, the magnetic momentum, you can say that interactions, and from that what you will get the hyperfine splitting. Okay, so that you will get new quantum number, which is known as hyperfine quantum number. So okay, and what will happen that the 3/2 and half will combine, and if you just do the angular momentum algebra, you will get F equal to 1, F equal to 2, using that 3 by 2 minus half is 1, 3 by 2 plus half is 2. Similarly, for the p half, you will get f equal to 0 and f equal to 1. So you please remember this, okay, or you just go through once again, okay, from the textbook of any quantum mechanics, okay, where you get this hyperfine level, which is actually extremely important to understand the experiment in these cases, okay. And these, whatever you see up to now, is all intrinsic to the atom. Okay, so they are actually there, and it depends upon how you want to look at what is the resolution of observation. So if you are these, as you understand, these energy separation is small, and if your detection resolution is not sufficient to resolve them, there's no point to understand them. Okay, but nowadays, what happened that your resolution is very high, you will be able to observe them separately. Okay, so it depends upon your intention of the experiment, and these are all there inside the atom, and it depends upon your detection resolutions. Okay. But there is something which you can control, and that is actually that thing is that once you have that hyperfine level, okay, that can have the different components. Okay, so that components can be understood as a for f equal to 1, you can say that mf equal to -1, 0, 1. Okay, for f equal to 0, f equal to only 0. So you'll get the different components, okay, and those are actually designed. They are inside the system, inside the atom, but you will not be able to see them unless you apply external magnetic field, which separate them out. So once you apply magnetic field, okay, if you have a magnetic field going this way, what will happen? That energy level plus mf from plus 1 mf will go down, and plus 1 will go up, and this 0, 1 will be unaltered. And what you see, the splitting in the energies. Okay, so that actually is possible using magnetic field. So you have to remember that using magnetic field, you can separate them out. And that is a very, very important one when you want to do for the pooling and trapping scenario, okay, which will be discussed in the last class, okay. Now, thing is that one more things that which you want to understand before I want to close this one is that what is the interaction, okay. So for that, what you saw that from atomic Hamiltonian, first you have to understand. This is an example for the sodium atom. Let me say that you have a nucleus, you have a core electrons that 1 square, 2 square, 2p6. Those are either in the gray region, and then outside that core region, you have the single electron. Let's say there is a 3s electron which is lying here. Okay, and you have an unoccupied orbital or state. Okay, which is 3p, and like that there will be many more unoccupied orbitals. So if we just consider the two-level system, okay, that means that we are choosing that whatever there in core that is frozen, okay, we don't bother about them, okay. Only thing that we have the level 3s and 3p available to us, okay, and we have a single electron, what it do, okay. So for that, what we can just do that, we can write that interaction, first of all, we can write the atomic Hamiltonian, okay. So if you write atomic Hamiltonian, which you can write easily in the sense that in the kinetic energy terms, there will be neutral. So this is for the electrons, okay. Kinetic energy terms, okay, for summation of all the electron. Then your nuclear attractions, okay. Then you have something very important that electron-electron interactions. So if you freeze that all the electron, okay, which are in the core, then you have like a hydrogen-like atom. You have only one electron sitting outside of the frozen core, okay. So you can just think about this term is not present because you have only single electron, okay. So here what you can just understand, you have the two terms, okay. You have the kinetic energy terms and nuclear attractions. So now what happened, you just calculate that using Schrodinger equation, time independent Schrodinger equation, you can calculate that what will be the wave function of the 3s orbital, what will be the wave function of the 3p orbital using the eigenvalue equation, which is known as Schrodinger equations. Okay, so if you use that, what will happen? You will get that eigen energies, which are nothing but the orbital energies, which you will get for the 3s and 3p. So let me designate them in terms of ground and excited G and E. Okay, so this will be in two-level system. G 3s orbital is a ground and 3p is excited. Okay, so that we are just designated G and E. So if you want to write in the bracket notation, okay, how do I write? Okay, this is Hamiltonian. So these Hamiltons, since there is some frozen part, okay, we don't bother about. Only we have a few degrees of freedom, that is ground state and excited state. And we want to write the Hamilton in terms of those orbitals on functions, okay, or bracket form, okay. So what we can write in terms of density form, okay. So in terms of density of the ground state, okay, so we'll have that since Hamilton represents the energy, okay. So you can just see that if you write in terms of ground state density, the coefficient of that will be nothing but your ground state energy. So when you are looking at the excited state density, that will come with the excited state energies. So what you will have that your total Hamiltonian, now you will be able to write in terms of the density of the state of ground state and excited state. Okay. Now what you can fix it, because now you want to have that relative changes of the energies, because you will shine the light and see that how this electron will go to the excited state. So that it depends upon the energy difference between the two states. So in that cases, we are only needed that energy difference, and we can set that ground state energy is 0. So once you fix that ground state energy is 0, we will be able to see only that you can write that atomic Hamiltonian is nothing but EE and your density state, that is density matrix, okay, with respect to the excited state. So that is your atomic Hamiltonian. And then what would happen? Then we will get that, as you know, that in the quantized form, we can write the radiation Hamilton is nothing but beta gal B plus half with the H cos omega energy for the light which is having frequency omega. So using these two, we would like to see that in the next class tomorrow, that how interaction Hamilton takes place. Once we understand that, then we'll try to understand that that effect in small cavity region, okay, where actually this radiation field is quantized, okay, if you place an atom, how the interaction takes place. Okay, so that will give a novel technique, and which will give a very good controlling power, okay, in subsequent experiment. I think I would like to stop today, okay, and look for some of the questions which I would like to answer. Okay. Thank you for your kind attention.
Okay, I think now it is a time for question and answers. Please send a message. You can send questions as messages.
Yeah, please use the chat box.
Yeah.
Okay, so one question from Raj Kumar. Do
Right.
the terms modes and state have the same meaning?
Sorry.
Like when we say a Fock state with n photons and a photon in nth mode, are they the same or different?
Yeah, that nth mode means that yeah, right, that you are at the nth quantized mode. Okay. So 1 minute, that is the difference is there. Okay, sorry. There is defined mode. Okay. So as you explained that, okay, here you are right, you are having that energy level n, but initially when we just discussed, okay, that quantization of electromagnetic field, okay, there actually we told that you can have a single mode, multi-mode, okay. So and what we are discussing, that mode is actually that defined mode of the electromagnetic field itself. Here is the defined mode of the quantization. Okay, so please bear with me. Okay, so I'm sorry that making it confused, that mixing of the two modes. Okay, so here is the quantization. When we are talking modes, it is a quantization mode. Okay, so level of quantization, which is different from the electromagnetic modes. Okay. So we haven't discussed the multi-mode quantization.
Yeah, I hope that makes that answer clear to the participant. So are there any other questions? Please send it to the chat box.
Any other question?
So is there any question from the YouTube?
No, sir. No questions.
Okay.
Good, Sunil, maybe we can close the session.
Yeah.
Any
yeah,
announcement
sure.
regarding the tutorial or anything?
So today there is a tutorial 3 p.m. So 3 to 4 there is a tutorial session. The assignment, the problem set was already shared with the students,
Yes.
participants. So I hope that they have tried to work it out and ready for the tutorial session in the afternoon at 3 p.m. So then 2 more classes to go.
Yes.
Tomorrow and the day after tomorrow. So I hope all the participants are enjoying the course. Today we had an excellent lecture on this photon modes and a single photon generation and things like that. And hope everyone could follow this.
Yeah, there was an earlier question also on this issue in one of the earlier classes. So I think those questions will also would have been answered today. So I think
So
this was a very useful session.
Very useful session. Yeah, very
Yes.
useful session. Yeah. So I think if there are questions, of course, in the tutorial session, everyone can ask.
Yeah, definitely.
Yeah. So then I would like to thank Sanjoy for another wonderful lecture. And all the student volunteers who are there for passing the questions to the speaker, and of course the IT team. They have been always with us, supporting us for all the
Yes.
during all the technical difficulties. Then of course, without participants, the session will not be useful at all. So of course, for all the participants who are very eagerly listening to all the lectures and making use of it, we thank the participants as well. So with this, I would like to conclude today's session. And then, of course, not today's session. Today, there is one more session, the tutorial session. Please be there to attend the session and make use of it. And we will see at 3 p.m.
And thank you too, Sunil, for taking care of all of this. It's
Well,
a great.
I didn't do anything.
It's a great task, and Sanjay has now prepared the participants for cavity electrodynamics. So I think
Cavity.
I think this is turning out to be a great course. So thank you, Sanjay. Thank you, Sunil.
Thank you, sir.
Okay then.
Okay.
Bye.
Bye. Bye.
Goodbye.
See you then.